Yeah, good evening everyone. So we'll wait for 2 more minutes, then we'll start the session. Yeah, we will wait for 1 minute, then we'll start the session. Yeah, so we'll start your session for today. So good evening everyone. So welcome to the Fundamentals of Combustion Live session series. So this is the week 12, the last session of this course. So we will go to the session. So this is a 2 hours course. So in the first hour we will discuss briefly what was discussed in the week 12. Briefly we will just discuss within the 1 hour, and then in the next 1 hour we will discuss some sample questions related to the week 12 problems and any other related assignment questions. So we will go forward. So in the brief outline of the course, we have almost completed different types of combustion processes, and so this in week 12, so we have dealt with droplet evaporation and combustion. Some last parts were dealt with that, and then combustion of carbon particle was the topic that was mainly dealt there. So we will go for the first hour session. Okay, so in the week 12 the major content was focused on combustion of carbon particles. So as we know, coal is a solid fuel commonly used in the power plants, and it's an heterogeneous in nature. So it was the the coal combustion is related to the power plants and other energy sources, where you can say that coal is an heterogeneous substance or heterogeneous in nature, you can mention. So this heterogeneity in coal was mainly, as discussed by professor, it is mainly consists of 4 elements, which include moisture, volatiles, fixed carbon content, and finally the ash content. So as you know, the moisture, since the coal or any of the fossil fuels, due to its old vegetation or any animal waste that's been underground for a very high pressure, under high pressure and temperatures, they may contain some amount of water content. That's what we see as the moisture in the coal. And in volatiles you may have different gaseous contents that been present in that. And for fixed carbon, if you see, this depends on how much time the coal was under the ground and how much time it was exposed to high pressure and temperature conditions, and this evaluates the percentage of carbon that is present in the coal. And ash content, it relates to the inert minerals or other things which are present in the coal. So basically there were, if you say an example of anthracite is an example of highest carbon content with 96 to 98 percentage of carbon. So Indian coals usually have a percentage of around 30 to 50% of ash as per the records. So these once you have a coal being given to you, you need to know what are the different percentages of these, each of the system. So we usually perform an analysis called proximate analysis. So this was explained. So in brief, if you see, it's also called a thermogravimetric analysis. So where the first step includes heating up the element up to 100 degrees centigrade. So heating up to 100 degrees centigrade, if you do, you can see that the moisture content that is trapped inside it will evaporate, and you will get a mass loss corresponding to the content of moisture that is present in it. So the mass of moisture that is being released out, you can weigh the thing and you can understand the percentage of moisture that was present in that. And in the second, then after that, further, if you are heating it to 350 to 450 degrees centigrade, if you make it hot, then you can see that the volatiles, which may include gases like methane or carbon monoxide or hydrogen, so these kind of gases, they will start coming out, and you will get a corresponding decrease in the weight for those corresponding volatiles also. And further, if you further step, if you want to find the fixed carbon on mineral material, which is usually referred as ash, will be left over as char. That is, once the combustion completes with the coal, you will remain with the char content that will give you the fixed carbon content and the mineral, whatever is material that was present inside the coal. So by this, if you remember the plot shown by the professor, you can see the mass and the temperature if you plot. So you have seen that initially it will be a temperature like this, then once mass will be decreased once you heat it to a temperature of say 100 degrees centigrade due to the moisture content being evaporated. Then further it will remain for some time constant, and then further it will go down at some 350 or 400 degrees centigrade. And further, if you are doing the combustion in an inert atmosphere, you can expect the curve to be almost nearly a straight line. Whereas if you are doing the combustion in an oxidizing environment, you will see that the system will further go down and oxidation will happen. So this is under oxidization medium if you do the combustion process. Further, this will happen at some 900 to 1200 degrees centigrade. So this kind of profile you will be getting if you plot the mass against the the temperature that is shown here. Then, so if you see the carbon surface, so if you take this as the carbon and this is the carbon surface, if you consider, sorry, I will write it just. So this as the carbon surface, that is the solid carbon coal. If you take the surface of that carbon coal, if you consider, you will see that from the external, the oxidizer is diffusing into the surface of the carbon, and the carbon, when you are heating it up, the fuel vapors or the carbon, any volatiles that are present will start coming out to the surface, and they will be coming out near the carbon surface. So that was related to the how you will be estimating the percentages of different contents that are present in a coal. And then after that, burning of coal is a rate determined. So the burning of coal, major part or the major content that decides the processes of coal combustion is depends on the fixed amount of carbon that is present inside the coal. And so mostly this coal combustion is mainly a surface reaction phenomenon. So it involves surface reactions, and based on the temperature and pressure conditions, you will get different species. So based on the temperature and pressure and temperature conditions, the content of different species, say you have oxygen, carbon dioxide, and water is the usual species that you find when you have a carbon combustion. So based on the temperature and pressure, you will be getting different percentages of them. And okay, so I will just briefly tell what are the different possible reactions that This was discussed there in the classroom, but we will just see what are the possible reactions. So you can see the carbon that is present inside the coal can go oxidize with oxygen, and it can form carbon dioxide, or 2 moles of carbon with the oxygen that is present, it can form carbon monoxide. Depending on the percentage and pressure conditions, this will change. Also, this carbon can react with the carbon dioxide that is being produced, and can result in carbon monoxide formation. And any water, the moisture content that is present, if it reacts with them, and it can even form the carbon monoxide, and hydrogen also can be formed through this. So these global reactions produce carbon monoxide in major content, so which participates in the gas phase homogeneous global reactions. So you can also have like reactions with carbon monoxide reacts with 1 mole of oxygen to form carbon dioxide. So these kind of reactions are also possible in this set of gas phase reactions. So in reality, the surface reactions are complex due to the nature of the char, and this phenomena is usually referred to as the intraparticle diffusion, is what it's being usually termed to. So this was major thing. And if we look into the simplified analysis, simplified models for the carbon combustion, if you look, so majorly 3 different models were proposed for this simplified analysis of a carbon combustion, where you have first one is the 1 film model, second is a 2 film model, and the third is called a continuous film model. So the major difference in a first 1 film 2 film models are, we will just discuss briefly that. So in a 1 film model, the complete oxidation is assumed to occur at carbon surface. So the complete oxidation happens at carbon surface, and up to which the oxygen penetrates. So up to the carbon surface, you can see the oxygen can penetrate up to that, where carbon dioxide is formed and maximum temperature is occurred. So and carbon dioxide is formed and maximum temperature is attained. Similarly, now if you go with the 2 film model, here you can see the carbon monoxide is, so you will have an inner surface and an outer surface. Here carbon monoxide is formed at the carbon surface. So if you take this as the carbon surface, here carbon monoxide is formed at the carbon surface due to the surface reactions between the carbon and the carbon dioxide that is present at the out end. And in the gas phase, if you see, you can form carbon monoxide. This reacts with the oxygen that is present in the system, so it will react with half mole of oxygen and it forms carbon dioxide. So in a thin, so this is the thin flame that we are referring to. So if you write it properly, you can see that this is the region where you have a thin flame being sitting, or across that you will see the carbon monoxide being reacting with the oxidizing medium and forming the carbon dioxide. And in a continuous film model, if you see, there is no distinct flame zone, and the reaction is assumed to spread over the boundary layer present over the carbon particle. So over the carbon particle, the boundary layer across which it is present, there will be no distinct zone, flame zone, or like this, as you have separate 2 zones being present in the 2 film model. You will be seeing as a complete set, you will be seeing there. So in analysis of the 1 film model, there were different set of assumptions were taken. So in that, important things were, we considered that the spherical carbon particle burn in a infinite stagnant ambient conditions is what we have considered the first one, and we considered that the burning process is quasi steady. So it does not change much with respect to time for a given instant at a different points in the system. And at carbon surface, you will see the reaction C plus O2 gives rise to CO2. So that was one assumption that was majorly true, and we say that the gas phase has three species. Mainly you have carbon dioxide, carbon monoxide, and oxygen. So these were the three different species that we consider, and we have majorly find these three species only for during the combustion of this system. And if you see the usual for easiness of calculation, we say that all the properties including the thermal conductivity, the specific heat for the system or for the material which we have, and the product density, so these are all taken to be constant for this analysis, and we take the Lewis number also to be equal to 1, and the particle we consider that it is at uniform temperature. So you will not have any temperature gradient within the carbon particle, and radiates the heat to the ambient as a gray body is what the assumption is, and radiate heat as a gray body. So that was the major assumptions that were taken. So if you see the structure of the variations, so say this is your flame surface or the coal surface, radius is RS if you say, and if you plot the temperature and mass fractions across the ordinate, and you have the radius in the abscissa. So if you see that your temperature remains Ts for surface temperature, it will remain at this temperature for some time, then it will have maximum, and then it will slowly decay down to the ambient temperature as you increase the radius from the surface of the coal. At the same time, if you see the oxygen concentration, you will see that it will come and diffuse, and it will be getting extent at the coal surface. It will not be able to penetrate into the coal surface. So if you see now, the carbon dioxide percentage will also slowly increase at this near the flame. Carbon dioxide thing will also increase at the surface, coal surface, it will be a maximum, and then it will be keep on decay. So now once you know the structure, you can write the mass and species conservation equations for this. Species conservation equations can be written. So the species and mass conservation equations include, say you have the surface here, say this is the radius of the coal surface, and you have the mass flux of carbon that is being coming like in this way, and this produces the mass flux of carbon dioxide that is being given out. Correspondingly, the mass flux of oxygen that is diffusing inside will come through this side. So now if you try to balance this, you will see that the mass flux of carbon burning will be equal to the mass flux of carbon dioxide minus the mass flux of the oxygen that is being sent. Similarly, if you are taking at some other radius, if at some other radius if you are seeing, you can see that this is the coal surface, and this is some radius, arbitrary radius you have chosen. So you will see the similar mass flux flow for this region also, whereas the mass flux of oxygen will be like this, and the mass flux of the net, it's not now the simple carbon burning is not only the mass flux that is present there, you have different gaseous products being also released. So the net mass flux at that point, at that region, if you equate, it will be equal to the carbon dioxide to the oxygen mass flux difference. So in a steady burning with no gas being no gas phase reactions, the mass flow rate of each species are taken to be a constant. Therefore, the net mass flow is equal. So this equation A and B, you can equate it when there is no gas phase reactions, you can equate them. So if you consider a global one step reaction, if you consider, say you have 1 kilogram of carbon reacting with S kilogram of oxygen, to form 1 plus S kilogram of carbon dioxide you have. This is the global one-step reaction. Here the mass flow rate of carbon can be used to calculate the mass flow rates of oxygen and carbon dioxide. So we can use this mass flow rate to determine mass flow rate of carbon dioxide and mass flow rate of oxygen. So the relation is simple. You have a mass flow rate of carbon dioxide will be equal to the total number of moles of the carbon monoxide times the mass flow rate of carbon. So if you take the ratios, you can clearly understand that. Whereas for the mass flow rate of oxygen, if you see, there are only S moles of oxygen that is being present there, so it will be equal to the mass flow rate of carbon burning rate that is being shown there. So once you receive, you can write the mass or the mass burning rates in terms of the mass flow rates of carbon dioxide and carbon oxygen which you have. So it is enough to solve for a one gas phase species conservation can be solved using these equations. So since oxygen is transported to the surface from the ambient by both, so oxygen is transported to the surface by both convection, that is the net flow, you can say, due to the net flow, and you have diffusion, which represents by participating in the reaction at the surface, participating at the reaction at the surface. So this is major thing that you can see. Now if you try to equate the net mass flux of the oxygen, so you can, since you have the relation now, you can just equate the mass flux of oxygen, and you can write that this mass flux of oxygen is nothing but the amount of carbon dioxide that's been coming out of the surface to the mass flux of the carbon oxygen that is being diffusing into the carbon surface times the mole mass fraction will give you this thing. And by using the Fick's law, you can write the gradient of this mass fraction of oxygen also you can write. So this entire term is nothing but the mass flux of carbon that we just wrote above. So you can write this mass flux of oxygen in terms of the mass flux of carbon burning. So it is, this S is nothing but the stoichiometric fuel air ratios that you need for the given reaction. So now you can, so this will be the mass flow rate of carbon. So you can put this into this equation, and you will get S times mass flow rate of carbon with mass burning rate of carbon is nothing but the 1 plus S times the mass flow rate of carbon times S times the mass flow rate of carbon. So you, once you equate this, you can write this S with, okay, so this S you can in order to convert the flux to the flow rate, you need to multiply it with the area. So you can just multiply this 4 pi r square as the surface area of the sphere into dr here. So here you will be taking the assumptions that it was a spherical thing. So finally you will be coming down to a first order equation wherein you have a mass burning rate of carbon times the mass fraction of oxygen will be equal to minus rho d times the area times the gradient of mass fraction of oxygen. This is nothing but equal to the minus S times m dot c. So now if you apply the boundary conditions where r equal to rs, this at the surface, you will see that the oxidizer oxygen is nothing but the oxidizer at the surface value, and r tends to infinity condition. If you see, the oxidizer is nothing but the oxidizer at infinity you will take, that is the ambient conditions you will take. So oxidation conservation equation can be integrated, and using these boundary conditions the mass burning rate of carbon can be determined. So using this equation, say C, on separating variables and integrating them, you will finally get a mass flow rate, burning rate of carbon as 4 pi rs times the rho d, and natural logarithm of, you will see the mass fraction of at the at the ambient condition to the oxidizer at the surface. So here the unknown is the mass fraction of oxygen that is present at the surface is the unknown quantity. So since oxygen concentration is dependent on the surface reactions, so we need to now consider the kinetics also that is present here. So due to the dependency of mass fraction of O2 on the surface reactions, say we have carbon plus oxygen gives rise to carbon dioxide. So assume that to be the first order and its rate depends on the oxygen concentration. We can write this mass flux of carbon burning at the surface as the rate constant times the molecular weight of the carbon into the concentration of the oxidizer at that time. So this Kc is nothing but, you can write from the previous knowledge, we can write A, it is nothing but Ae power minus Ea by Ru times T surface. So this oxidizer, in terms of the mass fraction, you can write them, since we know that oxidizer concentration is nothing but P by Ru by molecular weight of the mixture times the T. Now and you also know Pv is equal to nRuT. You can get the pressure values, say this is some C times RUT. N by V you can take the take it the mass concentration. So finally you will get the mass flux of carbon at the surface as the rate constant times the molecular weight of the cis carbon by the molecular weight of the mixture by the molecular weight of oxygen that is present there by P RUTS times the oxidizer at the surface. So this is one of the equations that will be useful. Now once we determine this kinetic parameters, so you can just write them simply as, so carbon is nothing but K kinetic, that is the kinetic parameter, and you have the oxidizer at the surface, mass fraction of oxidizer at the surface. This kinetic parameter, it depends on the pressure and temperature, and it depends also on the particle radius. It depends also on the particle radius of the system. So equation B is solved. So to get the mass fraction of oxygen at the particle surface, we do rearrangement, and finally we will come to a equation for the mass burning rate of carbon as 4 pi times Rs rho d ln 1 plus mass fraction at infinity minus mass fraction at the surface by S times at the surface. So here you can write this term as B, which is the thing, but the this is of the form now as a old evaporation thing, when you, if you remember. Now we take that ln 1 plus B, where B is very small, so you will get an equation to, you can directly write it as P there, and you will get the mass burning rate as 4 pi Rs times rho d I0 times infinity minus S by S plus S. So now if you convert it into an electrical analogy, you can say that the mass burning rate of carbon is nothing but the oxidizer of infinity minus the oxidizer of surface by the S of S divided by 4 pi Rs rho d. You can write it like this. This is nothing but the net difference between the mass fractions by the resistance due to diffusion. So this can also written as mass flow rate of oxidizer by the stoichiometric value, that is the S that you determine from the global reaction equation. So once you get this equation, you can now write the value. So you can just write for kinetically and to find the mass flow rate of burning rate of carbon, I0 infinity. If your surface at the surface, usually the oxidizer concentrations here 0, then you can put that value as 0 by the resistance due to chemical kinetics and resistance due to the diffusion process. Both you can add up. So this equation is important. So you can use this equation to find. So here at the rate due to the resistance at the kinetic due to kinetic can be is written as the form R S RU times Ts by 4 pi Rs times the molecular weight of the mixture times the rate constant times P. Whereas for diffusion resistance, if you write, it is nothing but S times IO2 at the surface by rho d times 4 pi Rs. So here in the diffusion, the unknown values of surface mass fractions of oxygen, and so unknown, we tried do an iterative procedure and we used to find them. Then the ratio of this, the ratio of the resistance due to kinetics and diffusion due to diffusion can be written as S plus S times the surface as RTUS times the molecular weight of mixture into P times the rho d mu c into 1 by Rs. So this is the equation that can be used if they are asking you to find the relation between the resistance due to kinetics and resistance due to the diffusion process. So we finally end up in 3 different combustion modes of operation. So in the 3 combustion modes, if you see, if the resistance due to kinetics is very less compared to the resistance due to diffusion, you can say that this is a diffusion controlled, and at this time this happens when your surface coal radius is large and pressure and temperature are high values. So you can write the mass burning rate of carbon as the mass fraction at the infinity times the resistance due to diffusion, and since if you don't have resistance due to kinetics, you can take that as 0. And the second mode is if your kinetics resistance due to kinetics is greater than kinetics is very greater than that of the diffusion, then it is kinetically controlled experiment where the radius is small and pressure and temperature are also low. Now the third case is when your resistance due to kinetics is approximately equal to the resistance due to diffusion. Then you see that the combustion is controlled both kinetically and by diffusion. By both things you will be able to see that. So this implies the mass burning rate of carbon is nothing but the mass fraction at the infinity by resistance due to diffusion, resistance due to kinetics, chemical kinetics, you can write that. So based on these values of resistance, you can explain how the reaction is proceeding, either it's a diffusion controlled or a kinetically controlled reaction it is. So in order to calculate the surface temperatures, energy conservation is required. So in liquid fuel combustion, what happened was, we know the surface temperature, we can tell a particular value that it can reach up to the boiling point of the system. But in coal you can't say that, so the surface temperature can be any higher value. So in the energy balance you need to be writing at the surface. So the energy balance at the surface, the energy balance at surface is written where you can see that the mass flow rate of carbon combustion at the enthalpy of that carbon by the oxygen times oxygen minus the mass flow rate of carbon dioxide times the enthalpy of carbon dioxide. This is nothing but this will be equal to the heat that is supplied from the surface. So if you draw a, this is the, say this is your cold surface, so you will have a mass flow rate of carbon and you will have an inlet enthalpy for this carbon. Similarly, you will have a mass flow rate out of carbon dioxide and enthalpy for carbon dioxide, and you will have a input for higher oxygen and an enthalpy for oxygen. So if you write this, this is the from surface to inside, this is the heat that is being sent, and this is from surface to the outside condition, so it can write it as ambient is goes, and here from ambient it comes to the surface. So here this will come here, and additionally you will have, so this is nothing but Q times S to ambient, and additionally you will have Q due to radiation. So once you know this energy equation, then you can write down the complete energy equation as mass flow rate of burning rate of carbon times the enthalpy of combustion, that will be equal to the constant times 4 pi rs square times dt by. So this gradient in you need to determine and then put the constraints over it. So this is the radiation term, 4 pi r square times sigma ts to the power t power. If you do that, you will get this equation. So similarly, this was seen for on solving. You will see similar equations in the liquid evaporation conditions also. So there the gradient, this dt by dr at the surface was written as z times mass flow burning rate of carbon by r square times t infinity minus ts, the exponential z m dot c by rs by 1 minus exponential of minus z m dot c by rs. So here the z value is nothing but the ratio of specific enthalpy to the conduction, 4 pi kg, that is being shown there. And if you see carefully, that boiling temperature for liquid evaporation was replaced by the surface temperature here. So that is the only change for this cold combustion on determining the gradient. So this expression for temperature derivative is used in energy equation to obtain a relation for carbon burning rate, and substituting these values into the unknowns m dot and mass flow rate of carbon, and if you put those values, so this is nothing but the surrounding. So finally, on substituting this, we get the mass flow rate of carbon times the heat of combustion will be equal to mass flow rate Cp of G times exponential of minus m dot C Cpg by 4 pi kg rs by 1 minus exponential of m dot C Cpg by 4 pi kg rs times T0 minus Ts plus epsilon s of 4 pi r square. This is the radiation term that is being I am writing here, surroundings times to the 4. So it is proportional to the fourth power of the temperature there. So this is solved iteratively to get a accurate values for that surface temperature values, and from the species conservation equation, if you see, you have the mass burning rate of carbon as the mass fraction at infinity minus the mass fraction of oxygen at the surface, that is usually 0 there, times the resistance due to kinetics and resistance due to the diffusion. resistance. So you will boil down to this final set of equations where you will get the mass burning rate of the carbon, which is shown here. Now, so this until now we were dealing with the one film model. Now a little small description of what was discussed regarding the two film model we will just discuss. So in a two film model, if you plot the structure graph, you will see that if this is the surface of the coal and if this is the thin flame that you have, and you say you are plotting temperature and mass fractions in the ordinate, and if you can see that the temperature initially remains here, then it goes to a higher value at the flame to Tf, and then it slowly starts decay. Whereas if you see for a two film model, we said that there is a high percentage of carbon monoxide that is formed near the surface, then it goes like this. This is not a straight line actually, so you will get a value. This will be coming like this. So this is the carbon monoxide that you have. Whereas if you see, the oxidizer will be coming like this, and it will be the oxidizer will be coming like this, and it will be coming here, and it will be decaying down there. So this oxidizer from infinity, it will go to a zero at the flame. Now if you see the carbon dioxide contents here, you will see that the carbon dioxide comes on and decreases near the surface. At the same time, here it will slowly decay down to the lower value. So this is the R axis that we can show. So carbon surface, at the carbon surface, carbon dioxide reacts with hot carbon as per the, so this at the carbon surface, if you see, the carbon reacts with the oxidizer to form CO2. So this CO produced at the surface diffuse outward and is consumed at the flame sheet by reacting with the oxidizer. By reacting with the oxidizer, it will, by the form CO plus half moles of O2, it gives rise to CO2, and assumed as infinitely fast rate of reaction, we are saying. And the temperature peaks, so you can see that the temperature has a maximum value at the flame sheet where you have. So the mass flow rate at the carbon surfaces and at the flame you can evaluate. So say we will just do that and we'll stop there. Say this is your coal surface that you have, and you have a mass flow rate of carbon that is coming in, you have a mass flow rate of carbon monoxide, and you have a mass flow rate of carbon dioxide that is diffusing from the outer to the towards the surface. So if you see at carbon surface, the mass flow rate of burning rate of carbon is nothing but the mass flow burning rate of carbon monoxide minus the mass burning rate of carbon dioxide at the inner region. So here I refers to the inner region of the surface. This is the inner region, this is the outer region. So I here refers to the inner region that is shown there between the surface and flame. Between surface and flame. So you can see that the mass flow rate of carbon monoxide is nothing but the mass flow rate of carbon dioxide times the inner and plus the mass flow rate in the mass burning rate of the carbon. So now for a reaction, say for a reaction 1 kilogram of carbon plus S1 kilograms of carbon dioxide, if you have, this will react to form 1 plus S1 kilograms of carbon monoxide can be formed. And if you see, the mass flow rate of carbon monoxide is nothing but the mass flow rate of carbon dioxide at the inner plus the mass flow rate of carbon. This is nothing but 1 plus S1 times the mass flow rate of carbon. So this is at the carbon surface that we have evaluated. Now if we try to evaluate it at the some distance from the surface of the coal. So if you see there, you can see at the flame you will have mass flow rate of carbon monoxide in this way. You will have mass flow rate of oxidizer being coming into this flame, and from the flame you will see the carbon dioxide is being released, and here you can see the oxidizer is pushed to from the inner zone towards the surface. Now if you try to equate that at the flame, if you try to equate, you will see that the mass flow rate of carbon monoxide minus the mass flow rate of carbon dioxide at the inner region will be equal to the mass flow rate of carbon dioxide at the outer region minus the mass flow rate of oxidizer. So the mass flow rate of carbon dioxide at the outer region is nothing but it's the mass flow burning rate of carbon plus mass burning rate of oxygen. So if you say for a reaction, say you have 1 kilogram of carbon monoxide plus S2 kilograms of oxidizer you had, this reacts to form 1 plus S2 kilograms of carbon dioxide, if you see. So the mass burning rate of oxidizer can be written as S2 times the mass flow rate of carbon monoxide. This in turn is nothing but S2 times 1 plus S1 of plus S1 times the mass burning rate of carbon. Similarly, the mass flow rate of carbon dioxide in the outer region is nothing but the mass burning rate of carbon plus the mass burning rate of oxidizer. This is nothing but 1 plus S2 times 1 plus S1 mass flow rate of carbon. So this is the two relations that you are coming down. So when you are trying to equate it, and then you have an iterative set of procedures that was taught in the class that will be used to find the different values and different flow rates, and you might be asked to find the surface temperatures after these reactions. So all these kind of things you can be finding it using those set of equations. So these was the brief a bird view of what was taught in the week 12 lectures. So we discussed regarding the one film model, two film models here. So and that inside that in two film model it is very complex once you go on increasing the structure, and if you consider more and more species into your equations, if you consider more of them, you will see that your solving number of equations increase and your more complex the system becomes. So I hope the parts everyone was able to some idea you got with this session. So we will go to the questions that we have with us. So we have dealt with the combustion of carbon particles here. So I will just see if recording is working fine. Okay. So now we will go to the next second phase of the session. We will go address the different questions that are here. Okay, so we will start with the first question. So the reaction at the carbon surface, and it is given as carbon plus oxidizer gives rise to carbon dioxide. So it's a surface reaction is shown there, and is an exothermic surface reaction or an endothermic surface reaction, or it's an endothermic recombination reaction, or it's an exothermic recombination reaction. So you can see that the carbon plus oxidizer gives rise to carbon dioxide reaction. This results in release of energy, and at the surface you can see that your temperatures are higher compared to that of the ambient conditions. This clearly states that there is some release of energy at these surfaces, and you can at these surfaces and this surface of carbon, you can see them, and this at this surface you will have the maximum temperature. So this means that you have an exothermic reaction that is being happening there, and this is resulting in increase in the corresponding temperature at the surfaces. So I hope that is okay with everyone. So the next question is, the rate limiting step in a coal combustion is burning off. So we said that within a coal is a combination of 4 different parts. So it is having moisture, it has volatiles, it has fixed carbon content, and it has ash. Now the rate limiting step in a coal combustion is nothing but it is the amount of is the burning of carbon that is present, because depending on the quality of carbon that you have, more time it will take for the carbon to get heated up to the required temperatures. So the slowest time scale that you see is the carbon burning time scale compared to all the other. So the rate limiting step will be the carbon coal combustion will be the rate limiting step when you consider this different set of heterogeneous components that were present inside the coal. Okay, so I hope that is good. So we will go to the next question. So this is two film model. So in a two film model, the question asks is, carbon dioxide is produced at the carbon particle surface. So we have drawn the structure diagram where we saw that this is the surface of the flame, and this is the surface of the coal surface, and this is the surface of the flame, or this is a thin film, you can say thin flame sheet. Now once you consider this temperature and mass fractions, you saw that at the near the surface of the coal, you will see that the carbon dioxide and carbon react to form the carbon monoxide that is present, that is being formed there. This carbon monoxide reacts with these remaining things, and it will form carbon dioxide at the near, it will make the carbon dioxide move out. So this was what we were, so this is what we see in the real experiments also. So these kind of complex models, once you start increasing different species and you find the percentages of these different species at different regions, you will see that the carbon monoxide percentages are higher at this near to this region of surface, and you will see that the carbon dioxide percentage starts increasing, it is higher there, and it will be going out reducing as it goes to the surrounding. So in a two film model, carbon dioxide is produced at the carbon particle surface. No, it is formed at the flame sheet. Carbon dioxide penetrates towards the surface. So the carbon dioxide will not be because it's at a high temperatures, it will be moving away from the flame surface. And the third point is carbon monoxide is produced at the carbon particle surface. Yes, so the carbon monoxide forms at the surface of the coal, and reduction reaction occurs at the surface issue. So reduction reaction is adding of the hydrogen or removing of the oxidizers. So you can see that doesn't happen there at the surface. So I hope, so you can go with carbon monoxide is produced at carbon particle surface. So I hope that is clear. So the next question is, one second. Yeah. So the mass flow rate of oxidizer is given in this question. the mass flow rate of oxidizer is given as 0.005 kilogram per second. Then the carbon burning rate. So he is asking us to find the carbon burning rate in kilogram per second is being asked here, and he is asking us to take a one film model. So in a one film model, our general global one step reaction was the global one step reaction that we considered was 1 kilogram of carbon plus S kilogram of oxidizer. This goes to 1 plus S kilogram of carbon dioxide. So now you know that. So from this equation you can say that the mass flow rate of carbon dioxide can be nothing but 1 plus S times the mass burning rate of carbon. So this implies that how much amount of carbon you had corresponding to the number of oxidizers, or the corresponding to the amount of burning that happened, it is equal to the number of moles into the number of mass flow rate of the burning rate of the carbon. So you can relate that in this way, and the mass flow rate of carbon dioxide and mass flow rate of oxidizer, if you see, it is nothing but S times the mass flow rate of burning rate of carbon. So now here he has given the mass burning rate of oxidizer is given, or the oxygen is given here. So you need to find the mass of carbon. So for that you need to find the value of S. So in order to find S, say you have the reaction C plus O2 gives rise to CO2. So this is a balanced equation. Now if you see there, the S is nothing but, say, the mass of fuel to the mass of oxidizer. So the mass flow rate of fuel to the mass flow rate of oxidizer, if you see, it is nothing but the, so number of fuel is nothing but 12. 1 second. Yeah, so this is the opposite way. So this mass of oxidizer by the mass rate of fuel, if you say, this will be equal to, so here it is oxygen is 16 times 2 by carbon is only 1, so it is 12. So you will get a value of, so you can cross it out and you will get 6, 3, so you will get 8 by 3, which is nearly of the form 667. So now once you get the value of S, now you need to find the mass burning rate of carbon. So this mass burning rate of carbon is the mass burning rate of oxidizer by S. So the mass burning rate of oxidizer is given there, it's 0.005 kilogram per second by the value of 2.667. So if you do that, you will get a value of 0.01875, which approximately something like 0.00188. So you can see that this is the value that corresponds to that. So from the one film model, once you are given a mass flow of oxidizer, and if you are asked to find the mass burning rate or the carbon burning rate in one film model, you can use this global step reaction and find the different values and get the required mass flow rate burning rates values. Okay. So I hope that was clear. So now the next question is the resistance to kinetics of surface reaction. Resistance to kinetics, that is the R kinetic of the, which we have seen earlier. This resistance of kinetics of surface reaction is directly proportional to. So if you remember, the equation was nearly S times RU TS by 4 pi rs, the molecular weight of the mixture times the constant into P. So now the question is, resistance of this kinetics is directly proportional to, so this resistance kinetics is directly proportional to 1 by P or the 1 by P, that is the P is the pressure mentioned there, so it is inversely proportional to the pressure. So he is asking, it is directly proportional to 1 by P of the system. So that is a simple one. Now the sixth question is, carbon particle combustion is diffusionally controlled. So carbon particle combustion is diffusionally controlled is what is asked here. So we saw that the resistance of, if the resistance of kinetics is very less than the resistance of diffusion, we will say that the system is, or the reaction is diffusionally controlled. So the requirement for that was, the surface or the radius diameter should be as high as possible, high, and the pressure and temperature are also high. So that means, so now the question is, carbon particle combustion diffusionally controlled when the particle radius is large, when it is small, or temperature is large. So you see that when your radius, particle radius is very large, you will get a, usually you will get a diffusionally control. Diffusionally control coal burning or coal carbon combustion, you will do it. Carbon particle. So I hope that was clear. So we will go to the next problem. Okay. So now we will see the next problem here. So estimate the burning rate of, so he is asking us to find the burning rate of a 250 micrometer diameter carbon particle. So we will just write the given here. So the diameter of carbon particle is given as 250 micrometer, and burning in still air of mass fraction of the ambient condition is 0.233 at 1 atmosphere is what he is saying. So this is data, and the particle temperature, so the particle temperature Ts is given as 1800 Kelvin. Then, and the kinetic rate constant, so the kinetic rate constant C is given as 13.9 meter per second. So assuming the molecular weight of the gas at the surface as, and he is saying the molecular weight of the gas at the surface is 30 kilogram per kilomole, then at what combustion regime it prevails is what the first one question is, and the second question is to estimate the burning rate. So two things we need to be determining in this equation. So we are being given the diameter of the carbon particle, then we are given the mass fractions at the ambient condition, then the surface temperature is been given there, and the rate constant values are also, kinetic rate constant values are given. So we will employ this electrical analogy over here. From electrical analogy, so to find the mass burning rate of the carbon, so the diffusional resistance is calculated from where the, so in order to find the mass burning rate, as you know, the mass burning rate of the carbon is nothing but the oxidizer concentration at infinity minus the oxidizer concentration at the surface by the resistance due to diffusion plus the resistance due to kinetics. So this is the equation. So in order to find these values, initially you need to know the values of resistance of the kinetics and resistance due to diffusion. So in order to determine that, initially we need the density is estimated. So we need to I estimate the density for using the ideal gas law, ideal gas, we say that the density is nothing but P by R T surface, where this R is nothing but the gas constant, it is nothing but universal gas constant by the molecular weight of the mixture times the surface temperature. So if you see that the pressure here is said is 1 atmosphere, which is nothing but 101325 Pascal, by the universal gas constant is 8314 joule per kilogram Kelvin, by molecular weight it is asked here to 30, it is asked here to take, and the surface temperature is 1800. So now if you substitute that, you will get 0.2 kilogram per meter cube as the density of the current mixture that we are gas which we are considering. And now you know the density. Now you need to find the mass diffusive values for carbon dioxide in nitrogen from. So this you can find corresponding to a, you can get the values from the table, or you can just use this equation here for this particular case. This is nothing but the temperature of the surface to 393 Kelvin, that is 100 degrees centigrade, to the power 1.5 you can use into the value of viscosity, or it is directly taken as 1.5 into 10% meter square per second. So now our surface temperature is 1800 by 393 Kelvin and power 1.5 into 1.6 times 10 power minus 5. So this now is nothing but equal to 1.57 times 10 power minus 4 meter square per second you will get. Now thus on the, if you remember, the in this carbon burning condition we are taking a one film model. So in that, if you see at the surface, at the coal surface, you will see that the oxidizer will come diffuse and it will be completely being used up there. You will not have any other oxidizer being left at the surface. So you can take the oxidizer at the surface to be equal to 0, or it's approximately equal to 0 you can take. So once you know that value, the resistance due to diffusion, this value is nothing but, equation was S plus the oxidizer at the surface by rho d times 4 pi Rs you can take. So if you see that S value you need to find. So since you are considering 1 milli model, we have just saw that C plus O2 gives rise to CO2. So that means your S value we got there was 2.667. You can use that, so you can get 2.66. Okay, it is actually 4. So 2.664, and this is nothing but 0 at the surface. And rho you have just found out, it is 0.2, and the D value is given, mass diffusivity value is, okay, mass diffusivity value we just determined over here, D, that is 1.57 times 10 power minus 4, and you have 4 times pi, and the radius, that is, you have a diameter of 250 micrometer, so 125 micrometer will be the radius you have. So now once you substitute these values, you will get the value of resistance to around 1.54 into 10 power 7 seconds per kg. Now you got the value for R diffusion you have got, it is around 5.41 times 10 power 7 second per kg. Now if you try to go with chemical kinetic resistance, if you are calculating the chemical kinetic resistance, if you calculate, you will see that the R kinetics is nothing but SRU times the surface temperature by 4 pi R square molecular weight of the mixture times the capacity into P. So this is nothing but the S value, you know, it is 2.664 times the universal gas constant 8314 times the burning surface temperature, that is 1800 Kelvin, by 4 pi times the radius of the surface, it is nothing but 125 into 10 power minus 6 the square into the molecular weight of the mixture. So it is given as to take 30 as the value, and the rate constant value is given over here, that is 13.9 meter per second is given there, times the value of P, that is 101325 Pascal. Now you substitute those values, you will get a value of around 4.81 into 10 power 6 seconds per kg is the value you will be getting. So now if you compare these values, the value of R diffusion and R kinetics, if you compare, you will see that the diffusion value is greater than the one order greater than the resistance due to kinetics. Thus the combustion is nearly diffusion control. So it is nearly diffusion control. So now we need to determine the mass flow rate of the mass burning rate of the carbon. So I will just remove this part over here. So now you can find the mass burning rate of carbon once you got the both resistance due to kinetics and resistance due to diffusion. So you know that this is nothing but the ratio of mass fraction of oxidizer to the mass fraction at the surface by the resistance due to kinetics plus resistance due to diffusion. So if you put that, you will get that the value of at the infinity is been given to you, it is like 0.223 minus at the surface it is 0 by the resistance due to the kinetics. So that value is we got 4.81 times 10 power 6 plus the resistance due to diffusion, so that is nearly 5.41 into 10 power 7. So now once you calculate it, you will get the mass burning rate to be around 3.96 into 10 power minus 9 kilogram per second. So if you want more accurately, you need to go with one more iteration, you can see, and you can see how much error you are getting in the values. So currently we will be doing that, we will just get the value. So if you see the solution, you can get that it is around 3.96 in 10 power minus 9 and it is diffusion control. So this is the answer you can go with. So I hope it was clear. Okay, we will go to the next question. So in the combustion of solid fuels, radiation usually plays a key role. So estimate the gas temperature required to keep a 250 micrometer diameter. So first thing is we need to find is the estimate the gas temperature required. For the purpose is to keep a diameter of 250 micrometer diameter burning carbon particle at 1800 Kelvin. So the given condition is you have a diameter of the carbon particle of nearly 250 micrometer and burning carbon particle has a temperature of the surface of 1800 Kelvin in that, for the first one, when there is no radiation, that is Ts is equal to the T surrounding, what is the values, and when there is, it's a black body radiation, if it is a black body radiation at 300 Kelvin, say you have, then, and he is asking us to take the similar conditions that was taken in question 7. So there we have determined the mass flow rate of carbon, burning rate of carbon, diffusion, thermal resistance due to the resistance is due to the diffusion, everything we have discussed there. Now once you know that, we will go with the this. So now, since energy equations we need to consider here, because we need to estimate the gas temperature that is being here. So the temperature can be estimated for the both the cases. So for that, we initially you need to know the values of the specific heat and the thermal conductivity. So these are available in the tables that are present in the Fundamentals of Combustion book by Stephen R. Turner. You can refer to that. So now for this, I will just write the values from that table. So the specific heat at 1800 Kelvin, if you see, its value is around 1286 joule per kilogram Kelvin, and the conductivity of this gas at 1800 Kelvin, so you can take the value of 0.12 watt per meter Kelvin. So since the particle is a black body, is mentioned in the question, the emissivity, when you are considering a black body, the emissivity is unity, and the heat of combustion of the carbon can be written as, so we will discuss that once you are doing. So the heat of combustion for this carbon particle, when you are considering a black body emission, so that delta heat of combustion will be 3 to 3 point it is 3.2765 into 10 power 7 joule per kg you will get. So these are available in the appendix tables of A, C. You can see that in the textbooks, and you can find these values. Now if you consider the first case, in the absence of radiation, we can, so that temperature at the infinity can be written as the temperature at the surface minus the heat of combustion by the specific heat of the gas times 1 minus exponential of minus burning rate of carbon times the specific heat of gas by 4 pi Rs into kg, that is the burner the carbon cold surface radius and exponential times minus mass flow rate of carbon Cpg by 4 pi kg Rs. You can go now in order and evaluated using the burn rate. So from the previous question, we know the burn rate value is around 3.96. we have the burn rate of 3.96 times 10 power minus 9 kilogram per second. So now if you substitute these values over here at the T infinity, the surface temperature is given as 1800, delta Hc is 3.2794 times 10 power 7 by the specific heat is 1286 and 1 minus exponential of, so mass burning rate, you know, it is 3.96 times 10 power minus 9 into specific heat, that is 1286 by 4 pi, radius of the surface is nothing but 125 into 10 power minus 6 into kg is 0.12. So that by exponential of minus 3.96 times 10 power minus 4 into 1286 by 4 pi times 125 into 10 power minus 6 into 0.12. So that you can just do the correct values. So finally it should be coming nearly to 698. So now the value of T infinity is around 1102 Kelvin. So this is the case 1 without radiation. Now when your surrounding temperature is at 300 Kelvin, so in the second case, when surrounding temperature is at 300 Kelvin, then you can write the radiation loss. The heat loss due to the radiation can be written as epsilon, that is the emissivity, times 4 pi rs square, that is the area, times the Stefan-Boltzmann constant into surface to the power 4 and surroundings to the power 4, you know. And for the emissivity, for the black body radiation, it is 1 into 4 pi times the radius of the surface is 125 into 10 power minus 6 square into Stefan-Boltzmann constant is 5.67 into 10 power minus 8, and the surface temperature here given is 1800 Kelvin, and the surroundings temperature is taken as 300 Kelvin is given. So if you substitute that, you will get a value of 0.1168 watts. Now this is the amount of heat that is released due to the radiation. Now the chemical heat release. So if you see the chemical heat release, this is found by the equation mass burning rate of carbon into the heat of combustion. So it is nothing but 3.96 times 10 power minus 4 into heat of combustion is nothing but 3.276 by 10 power minus 7. So you will calmly boil down to 1.299 watts you will get. Now the energy conducted from the particle surface is then found out using the conduction equation. So you can just the energy balance that we have carried out. So the energy balance which we carried out can be used out here. So I will just take out this value. So this was the answer for the first. So we will complete this here. So I will just move it up. So this was for the first condition. Okay. So now the energy conducted from the particle surface is then shown as the heat conducted Q dot is conducted is nothing but m dot c delta h of c minus Q radiation. So this is nothing but m dot c into delta hc can be written as delta hc is nothing but m dot cp into dt. So it is cpg times exponential of minus m dot c cpg by 4 pi kg rs by 1 minus exponential of minus m dot c cpg by 4 pi kg rs into, now you take the temperature difference common, so this will be equal to T into Ts minus T infinity. Now once you get that value, you can now solve that. One second. Yeah, so now you know the values of m dot c, which is nothing but 3.96 into 10 power minus 4 times the asking us to find that. So delta hc you know it is 3.2765 times 10 power 7 minus, okay, so m dot c, you know, cpg is the specific heat values, so that is given there, 1286 1286, so times exponential of minus 3.96 into 10 power minus 4 into this 1286 by 4 pi times kg, so this kg value is given there as 0.12 times the radius of this in micrometers is given as 250, so it is 125 into 10 power minus 6. Now you substitute the same values here also, this 3. Okay, 1 second. Sorry, 1 second. Yeah, so once you get that, you can put the value now to 3.96. Just clear it off clearly. So it is nothing but 3.96 times 10 power minus 4 into 1286 by 4 pi into 0.12 times 125 micrometers if you substitute here. So you know the surface temperature that is given here minus T infinity. So the total heat release and this m dot f and q radiation values you know, so you can use that. So chemical heat release is 0.1299 minus the radiation value, it is 0.11868 watts it is. So once you substitute all these values, finally you will get the value of T infinity to be around so the value of this comes to be around 1730 Kelvin. So you can just substitute it and check these values, you will get the required both, so with radiation and without radiation is being asked in the question, so we have just looked into that. and this is 1002. So the answer will be 1102 Kelvin and 1730 Kelvin will be the values that you need to be showing. Okay, so I hope this part is clear. So I will just check if recording is going correctly. Okay. So we will go to the next question. Okay, so the question asked is, assuming the diffusion control combustion, so is diffusion control combustion is same and identical condition. So here the mass fraction of oxidizer at the ambient condition is given here, and comparing the burn rates predicted by the one film. So he is asking us to compare the burning rates or the mass burning rate of carbon with the one film model and the two film models, how it will be. So we need to find the ratio of the burning rates between two film to the one film. So that's the question there. So if you remember, the burning rates for both one film and two film model can be simply written as, in short be written as the mass burning rate of carbon equal to 4 pi Rs times rho d ln of 1 plus Bm. So this is Bm is here refers to the number. Yeah, so only thing difference there in this equation for one film and two film is the Bm value. So for the two film and one film bond, since remaining all are nearly all constant values, you can write the ratio, that is the mass burning rate of carbon with two film by the mass burning rate of carbon with one film is equal to, since it's proportional to the logarithmic of 1 plus Bm times the logarithmic of 1 plus. So in two film model, you can see that the carbon dioxide is what is being present at the flame sheet, whereas for the single film model, you will see the oxidizer is being present there. So this equation can be used for equating the values. So we need to now find the transfer number of carbon dioxide with this, and we need to evaluate that. So the transfer number for carbon dioxide, so the equation relating to that is, it will have 2 times the mass fraction of oxidizer at the ambient minus the difference of the S minus 1. So S is the stoichiometric values that you are having by the S at the S value. So that refers to the, since you are using carbon dioxide, okay, these values I will just clear up. I will just write the complete equation times the carbon dioxide of the surface by the surface minus 1 plus this S minus 1. So here this will be the S of the carbon dioxide when you are using it. So this times S times multiply times the carbon dioxide at the surface. So here you consider the global reaction. When you consider the global reaction, you can see that when you are considering the two film model where you will having carbon dioxide, so in that the carbon dioxide thing, you will see that 1 plus S is your SS there, that is, which implies 1 plus the S number of mass fuel flow rate to the air flow rate. You can, when you get it, this for this given single step global reaction, you got it around 2.664. So the total value will be 3.664 will be the value of S subscript S. So and the normal value of S, as you know, this is nothing but the mass fuel by the oxidizer, the oxidizer by fuel. So it is nothing but 16 times 2 by 12. So this you will do it at 2.664. So these are the two values here. Now if you substitute these values at the equation that you have, BCO2 times m is 2 times the mass fraction of the infinity is given as 0.233 minus the S value, that is 2.664 minus 1 by. Okay, so another important thing that you should be noting down here is this mass fraction of carbon dioxide at the surface. So this value at the surface, you will not be having any much of the carbon dioxide being formed. It is near the flame. When you consider the two film model, you will be seeing that the carbon dioxide is mostly formed at the near the thin flame sheet condition region. So now this will be just multiplication by 0, and this value of SS will be, as you know, this we just got 3.664 minus 1 plus this whole fraction into the 0. Now once you substitute these values, you will be remaining with only this fraction, that is 664 you will be coming up. Now once you substitute those values, you will get a value of this for this transfer number of around 0.175. So that is one of the equation. Now for when you consider the single film model, one film model, when you are considering, once you are considering the one film model, there the transfer number BO2 of m, when you consider it, you will see the mass fraction of infinity minus the mass fraction at the surface by the value of S at the surface. So it is the oxidizer at the surface to the value of the S at the given point. So that value, if you consider, so the value of at infinity is being given as 0.233. So the oxidizer at the surface. So when you are considering a single film at the surface of the cold surface, you will see that the mass fraction of oxidizer will not be able to penetrate inside. This fraction will be completely going to 0 at that point. So it will be equal to 0 there, and the value of S for that point is 2.664 plus the value of mass fraction of oxidizer. So this value is the mass fraction of oxidizer at the surface, and S value is what we have written here, and this will be equal to 0. So once you equate it, you will get to a value of around 0.0875. Nine 840. So now, so finally we need to find the ratio of burning rates. So finally the question asked is to find the ratio of burning rates of when you are considering a 2 film and 1 film model. So the ratio of the mass of burning rate of 2 film by the mass of burning of 1 film, if you consider, this is nothing but the ln of 1 plus BCO2 of m is nothing but the value that we got here at A, and BO2 at m is nothing but B. So this is ln 1 plus 0.175 by ln 1 plus 0.0875. So this value, if you see, this will be boiled down to 1.92. So the question asked is find the ratio of the burning rates of 2 film model to the 1 film model. So that value comes to around 1.92. So I hope this question is clear. So we are done with the questions for this week. So we have come to an end to the course series where all the courses related to all we have tried to complete fundamentals of the basics of all the combustion processes and lot of basic key things that we need to be knowing when you are studying a combustion. We have learned. We hope we could cover a lot of things, and this hope this live session was a useful for at least for some people. It might be useful, I believe. So this is the week 12 and this is the final class, and I hope your exams are nearby, and I wish everyone all the best for your exams, and prepare well, and I hope you will get all the best for your exams, I can tell that. So in the week 12, so this was the main coal combustion of a carbon particle. So mainly the solid fuel combustion is what was dealt mainly, and yeah, so I will just wait for some 2-3 minutes if anyone wants to join or any questions are there, else we will stop the session. So I hope these live sessions were helpful for some people, and if any questions are there still, you can post it in the discussion forums. We will try to answer them. So one of the questions that were posted in the discussion forums previous week was that related to some of the assignment questions, where 2 questions were given, and I don't remember the name, but the person has asked why we are using separate methods for doing the problems separately. So the questions, if you see properly, the given data that does not include pressure or any other conditions in one of the questions, so you can't find the other related data without the values being given there. So you need to go with a specific method that's been discussed in the assignment solutions. If you see, you can see that you need to go with that process, since you don't have the other details that is been given for for that specific question. So that is one thing that needs to be clarified in the discussion forums that was posted. So that main difference was that the data that was given is not sufficient for you to go with the same procedure that is been implemented in the class there. So you need to go in a different way. For that, you need to solve it in that way to get the answer. I hope that was helpful. Yeah, so if no more questions, we will stop the session, and thank you everyone, and all the best for your exams. Thank you.